Okay, let's begin. Now, today we'll continue with power series. I'll start with some reminders since we had a weekend. Okay, so we'll represent functions. Okay, so here the basic tools we had were the following. So if we have a power series like this, n equals 0 to infinity, Cn x minus x sub 0 n, then the derivative of this is equal to term by term differentiation. N minus 1. And similarly for integration. And also similar for integration. And moreover, both series, the series inside and this series, the derivative and integral, have the same radius of convergence. Only the endpoints may change. You have to check the endpoints separately. And using this, we started with the geometric series. And this holds for x less than 1. Okay, so now playing with this and integrating, differentiating, we obtain different functions. For example, we put minus x, or which one? Okay, put minus x for x and integrate both sides. You integrate it from 0 to x, okay, from 0 to x, and we obtain, so let me write this because we already did this one. Okay, so we'll have the ln stuff for this thing. So here, ln 1 plus x is equal to x minus x squared over 2 plus x3 over 3. So this goes on like this, minus 1 to the power n minus 1, xn over n. Okay, and this thing converges for, you see, this one converges, and this one diverges at the endpoints. But this one converges at one endpoint. So at minus 1, obviously, it diverges because this side doesn't make sense. Okay? And this part becomes minus the harmonic series. And x less than or equal to 1. Okay? So you see that on this side, if you put x equals 1, it's an alternating harmonic series. It's the alternating harmonic series. It converges. This side, when you put x equals 1, ln 2, it makes sense. There is a theorem checking what happens in these cases. It's not always automatic that if this side converges at the endpoint, it will be equal to this side. You have to check a few things. With real variables, it's easy. You have Abel's theorem, which says that if this is continuous at the endpoint, if this is continuous at the endpoint, so if you approach to plus 1 from the left and this has a value there, in this case this is continuous, so then they will be equal. Okay, so this equality at the endpoint follows from Abel's theorem, which we didn't cover, but in case you want to be precise, that's why we have equality there. Otherwise, this equality at the endpoint is not automatic. So from that, once we establish this, you obtain ln 2 as 1 minus 1 over 2 plus 1 over 3 plus, minus, okay? So alternating harmonic series adds up to ln 2. We also had another substitution. So next, we substituted x square minus x square for x in the geometric series, and integrated to obtain, you see, that's the that's the ln part, arctangent part. So let me just copy it from somewhere here. Okay, so where is that? Anyway, okay, let's do that. I have 1 over 1 plus x squared. Okay, so I have 1 plus x squared. Well, I put minus, right? 1 minus x squared plus x to the 4 minus x to the 6 plus etc. Okay, so integrate, you get arctangent arctangent x. So this is equal to x minus x cubed over 3 plus x5 over 5 minus Emre Bey, bu bilgisayar söyleniyor herhalde. Bunu nereden kapatacağız? Ben düğmesine bassam olur mu? Yani bir program çalışıyorsa bozmayayım diye. Okay, so this goes on like this to the power n x to the 2n plus 1 over 2n plus 1. Okay, so this, you see, this converges when x is equal to minus 1. So this becomes harmonic series. So for minus 1, this doesn't converge, but when x equals 1, it's alternating series, so it converges. Okay, so again, we picked up an endpoint here. Okay, so this is continuous around 1, in particular when you're approaching from below. So you have equality there. Okay, so here, for example, putting arctangent 1, so this allows us to put x equals 1. We obtain an expression for pi over 4. So 1 minus 1 over 3 plus 1 over 5 minus etc. Okay, so this is a nice expression for pi, but it converges very, very slowly. So you need hundreds of terms to add before you get a few digit approximation. So you try something else here. Okay, so for example, if you put for x, so what is the tangent of pi over 6? Okay, so that's what, 1 over square root 3, right? So if you put 1 over square root 3 here, or in particular here you will have pi over 6. But here now 1 over square, instead of x, you are not putting 1, but you are putting 1 over square root 3, which is very small. So you take successive powers of it, it goes to 0 very fast. So here you obtain a series which converges very fast. So that's a better approximation for pi if you want to calculate pi using these things. There are more entertaining ways of obtaining fast approximations for pi, but for that I refer you to Google and Wikipedia. Okay. Okay, so that was what we did. Sometimes we use this again. This is the only tool we have. We just exploit it. For example, we can solve a problem like this using this. So what is the, find the sum. Okay, so for example, this one. So problem, find the sum, summation n equals 1 to infinity n square over 2 to the power n. Okay, so out of the blue, this doesn't make sense. But here you recognize that except for this n square, this is a geometric series. Okay, so somehow you must start from the geometric series. So this 1 over 2 will be your x. Okay, so you can start seeing this as summation of n square x to the n. Okay, because you have n here. So how do you obtain n square in front of this one? Okay, so you do step by step. First, how do you obtain n? Okay, so to solve this, first we recognize, so we find out what summation n xn is, then summation n square xn, okay, and put x equals 1 over 2 here, okay, in the last one. Okay, so let us see how we can do this. Now, first it looks obvious. If you take the derivative of the geometric series, you get n in front of x to the n minus 1. You are missing 1x. Well, that's easy. You multiply everything by x, you obtain this. So now that it worked, we take the derivative of this. We obtain n squared x to the power n minus 1. We are missing 1x, so we multiply everything by x. So we obtain this. But meanwhile, when we are doing this, our function is this. So what did we do? We took the derivative of this, multiplied it by x, took the derivative again, multiplied by x. So the left-hand side is a well-defined function. Okay, in that function, we put x equals 1 over 2 and obtain that sum. So let's see how that works. So here I did the calculation, so let me start with these. Okay, so we have 1 over 1 minus x equals 1 plus x plus x squared plus x to the n plus etc. So everything works for x less than 1. Let's keep that in mind. From here to here, differentiate. So you have 1 over 1 minus x squared, right? So this is 1 plus 2x plus 3x squared plus nx n minus 1. Now we multiply this by x. So x over 1 minus x squared is x plus 2x squared plus 3x cubed nx n plus, okay. So then we take the derivative of this. Okay, so for, I have all the calculations here, so let me just write. Then differentiate again. So what did I get after I differentiate? I hope this is correct. 1 minus x cubed, okay. So what you have here is 1 plus 4x plus 9x squared plus n squared x n minus 1 plus. Okay, so I'm missing just 1x. So finally I have x 1 plus x 1 minus x cubed is equal to 1 plus 4x squared plus 9x cubed plus n squared xn plus. Okay, so this is precisely what we have here, except that now I have x instead of 1 over 2. So I just put 1 over 2. Okay, so put x equals 1 over 2. So here you get 6, and here you get 1 plus 4 over 2 squared plus 9 over 2 cubed plus n squared over 2 to the n plus. So this was precisely what we wanted to obtain, and it turns out that it's equal to 6. Okay, so we did those. And okay, so we also did this one.
Why did left first row as R?
Huh? I took the derivative of this. I have 1. And here also I have 1.
But we multiplied with x.
Here, okay, so x. So this is 1 over 2. Okay, so my calculations were correct, but this one was wrong. Okay, so another use for these things, for power series, is the following. Again, you see, for the last half an hour, we are exploiting only the geometric series. Okay, so we didn't do anything new. So if you have just one tool, you get the most out of this. So another problem where we exploit geometric series is the following. So for example, this one, approximate 0 to 0.5 dx over 1 plus x to the power 5 with an error strictly less than 10 to the power minus 6. So here you can okay, so here you can put any error you like. So you see that we don't have a nice antiderivative for this thing. So our best hope is to approximate these things. And here we exploit again the idea of a geometric series. Instead of 1 over 1 plus x to the 5, we expand this as a geometric series and then use the fact that I can pass the integral to each term separately. Okay, so I can integrate each term now. Now each term is easy because each term is x to the power something. Okay, so I integrate that from 0 to 0.5. Since I have plus here, the geometric series will be alternating. After I integrate and put numbers, I will obtain an alternating series. And for alternating series, I know how to approximate. If you use n terms, the error made is in absolute value strictly less than the value of the absolute value of the n plus first term. Okay, so that's what we will do here. So that's the strategy. Okay, so 1 over 1 plus x5 is equal to 1 minus x to the 5 plus x to the 10 minus, okay, so let me write in general term, minus 1 to the power n. So this is after the integral. Before the integral, I just have the term x to the power 5n. Okay, so this, I have to remind myself where this is valid. So I check that 0.5 is in this interval, so I can continue. Okay. Integrate from 0 to x. Okay, so from 0 to x, so that the constant term, when you integrate something, you'll get an integration constant. So in our case, when you integrate from 0, the integration constant will be 0. So when we integrate this, we'll have 0 to x dx over 1 plus x to the 5 is equal to, I'm integrating this term by term. So this is x minus 1 over 6 x to the 6 plus, so the general term is n 1 over 5n plus 1 x to the power 5n plus 1. So again, it probably again converges at one of the endpoints, but we are not interested in that. We are doing this in the middle, 0.5. Okay, now put x equals 0.5. Okay, so we obtain the following. Okay, now we obtain the following value, 1 over 2 minus 1 over 6 plus times, I have to put the x there, 1 over 2 to the 6 plus 1 over 11, 1 over 2 to the 11, minus, etc. Okay, so I have this. So let me write the general term, because we'll use that. 1 over 5n plus 1 1 over 2 to the 5n plus 1. Okay. Now this is an alternating series. We want to see how many terms we need. Okay. So this is an alternating series. The error made by using the first n term, is less than the absolute value of the n plus first term. Okay? So we force this to be less than 10 to the minus 6. Okay? So if this is less than this, then the error I'm making by using the first n terms is less than this. So that's the trick, small trick we are using. Okay, so what is the n plus first term? So n plus first term is 1 over 5n plus 6 times 1 over 2 to the 5n plus 6. Okay, so I force this to be less than 1 over 10 to the 6. Okay, so in these cases, you don't try to solve this algebraically because it's horrible. You see, you have exponents and here, so you don't expect to get a useful solution, and nobody needs the useful solution. For example, you get the solution as 5.78, etc. Who needs those 78? You'll take 6 anyway. Okay, so here you try. You put n equals 1, 2, 3, or if you are lucky, you just put the correct n, and you see that for some n, it works. Okay, so here, in fact, okay, we find this n by trial and error, okay, by substitution. N equals 2 works, n equals 2 gives. Okay, you try small n here because you see you are raising 2 to the power 5 times something plus 6, so it's a huge number. So you try 1 or 2. Okay, I tried 2 and it worked. This gives 0.95 on this side. Okay, something here divided by 10 to the 6 for some. Okay, when you calculate these things, that's what I got. I don't after simplification. Okay, 10 to the 6, and this is less than 1 over 10 to the 6. Okay, so you use the first. So for some reason, I use the first 3 terms here. Okay, so we use the first 2 terms, but that's not. So this is 0, right? This one, where is the general term? This is 0, this is 1, this is 2. Okay, so this corresponds to n equals 0, this corresponds to n equals 1, this corresponds to n equals 2. So we use the first 2 terms, means that we use this part. Okay? So we use the terms corresponding to n equals 0, 1, 2. Okay? And the sum is, okay, so for the 33,619 over 67,584, or if you like, this is 0.497440, etc. But you see the error, since the error will probably affect this, so this can be 3 or 5, but this part will never change. Okay, so you have an exact 4-digit approximation for this one. Okay, so this can be this because this error is changing this one, okay? So when this one changes, if it goes up, okay, this will stay. But if it goes down, this will be 3. So we are not sure about this, but this part is correct. Okay, so this is one way of using power series. Actually, not power series. We are using only geometric series. Okay, so let's pass to the other way around. Now, obviously, we cannot generate all the functions using geometric series. The main interest is starting with a function and assigning a power series to it. And if we are lucky, there will be some alternating things here. If we are not lucky, there's a nice theorem saying that even if all of them are of the same sign, if you stop here, what is the error? Okay, so that's the big theorem, Taylor's theorem. Okay, so let's pass to that topic now. Okay, I'm erasing this now. Okay, so this is now Taylor series. So assume that we have a function. Assume that f of x f of x is a function. So this is c0 plus c1 x minus x sub 0 plus cn x minus x sub 0 n plus, and this is true for all x with x sub 0, x minus x sub 0 less than some r. So at this point, we don't bother to check what happens at the endpoints. So suppose you see that every power series defines a function in the interval of convergence. Now we call that function f. So we observe the obvious things. F of x sub 0 is equal to c0. Okay, so that's good. Now, if I take the first derivative, this one is killed. This one is killed. I'll have c1 plus other things, each of which has x minus x sub 0 in it. When I put x equals x sub 0, they will be all killed, and I recover c1. Okay, so I take the first derivative of this. This is equal to, this is c1, 2c2 x minus x sub 0 plus 3c3 x minus x sub 0 square plus n cn x minus x sub 0 n minus 1. Okay, so I have this. And now I can recover this. This is x, f prime x sub 0 is equal to c1. Okay, so all of these things are killed. I take one more derivative. So I'll take infinitely many derivatives like this. So this time this is killed. I have 2c2 plus 2 times 3 times c3 x minus x sub 0 plus n minus 1 times n times cn x minus x sub 0 n minus 2. If I evaluate this again at x sub 0, I'll get 2c2. Okay, so until I get here, I have to take n derivatives. If I take the nth derivative, I'll have n factorial here. Okay, so we patiently do these things, and we see a pattern. The pattern is that if I take n derivatives, here I'll have n factorial times cn plus, what do I have? I have 2 times up to n plus 1, x minus x sub 0 plus other things. All other things are something time are of the form something times x minus x sub 0. Here I forgot to put cn plus 1, x minus x sub 0 plus. Okay, now if I put x sub 0 here, I'll have n factorial cn, and all of these will be killed. Okay, So I checked that this is actually consistent with these things, and even with this one. Okay, so this one is the zeroth derivative of f at x sub 0. This is equal to 0 factorial times c0. 0 factorial is 1 for two reasons. First of all, in combinatoric calculations, every time you have 0 factorial somewhere, it behaves like 1. Okay, so you try to understand why it behaves like 1. Okay, so first of all, 0 factorial is not defined, but you do calculations, and symbolically, somewhere, if you end up with 0 factorial, normally you wouldn't write that. But if you write 0 factorial there, it behaves like 1. So you try to understand why that is the case. You find out that there is this gamma function, which is continuous differentiable. And it at the integers, at the nth integer, the value of the gamma function at n is n minus 1 factorial. Okay? So gamma 1 is 1. Gamma 1 corresponds to symbolically 0 factorial. So that's why you safely write 0 factorial as 1. So it's not, at this point now, it's not a convention, it's a fact. Okay? Okay, so you see that this pattern repeats. So we understand all of these coefficients. So it turns out that our f of x can be written as, so we are talking about this f of x, okay? So we already started with a function which is represented by a power series. We discovered that the power series, the coefficients of the power series are nice. Cn is equal to the nth derivative. Okay, so the nth derivative at x sub 0 divided by n factorial x minus x sub 0 n. Okay, so this is x minus x sub 0 less than r. Okay, now we ask the question backwards. Now we ask this backwards. Okay, given a C infinity function f, we can write the right-hand side. We can write summation n equals 0 to infinity, the nth derivative at x sub 0, x minus x sub 0 n. Okay, C infinity function means that all derivatives exist, okay? For this thing to make sense, I should be able to take derivatives of f infinitely many times. I end up with this thing. Now I start with the arbitrary C infinity function. I don't know if it is equal to a power series, but I can write this power series. Okay, so this power series makes sense. I have the function f makes sense. Do they agree? Okay, so that's the question. First of all, does this converge? So first question, does this converge? Okay, and two, if it converges on, you see that a power series converges on an interval symmetric around x sub 0. So if it converges on x minus x sub 0 less than r, does it converge? Does it converge to f of x there? Okay, so f of x may be defined at a larger interval, but the series may converge only at a small interval. Okay, example 1 over 1 plus x squared. Okay, so that's a geometric series, so it converges only for the absolute value of x less than 1, but 1 over 1 plus x squared is defined everywhere on the real line. Okay, so the reason for this discrepancy is all of these things actually take place in the complex plane. In the complex plane, 1 over 1 plus x squared is not defined at plus or minus I, Okay, so then convergence is a circle that grows until it touches the first singularity. Okay, so first singularity is at I. So the radius of that circle is 1. Okay, so when you restrict everything to real line, you only see from -1 to +1. Okay, but anyway, that's the reason why we ask this. F of x may be defined on a larger interval. If this series converges at a smaller interval, then do they agree there? Most of the nice functions we face in everyday life, in our everyday life, for those things, the answer to these things are yes. Okay, but for most of the functions, the answer is no. Okay, you have functions for which this thing does not converge at all. It may turn. We have ugly functions. No one has, I think, seen it, but theoretically we can show the existence of many such functions where this thing converges only at x equals x sub 0. And I'll give you an example in the. It's an exercise in the book. We have a C infinity function whose Taylor series is identically equal to 0. All derivatives are 0 at x sub 0. But obviously the function is not 0, so they don't agree. Okay? So we are only interested in nice functions for which the Taylor series converges on some interval to the function. Okay? So they deserve a special name. So let me first of all give these names, and then we'll check what we know about this theory. Okay. So for a function f, so Tnx equals f of x sub 0 plus f prime x sub 0 x minus x sub 0 plus, so I'm writing this, the first n terms of that series, x sub 0 over n factorial x minus x sub 0 n. This is a polynomial of degree n. Okay, so this is called the nth degree Taylor polynomial of f around x sub 0, but we don't write all of them here because the only time you need this name is you start with an f, so everybody knows what f is. You start with x sub 0, so these things are fixed in your calculations, and you write a polynomial. So this is the nth degree Taylor polynomial. Okay? This, if the function is C infinity, then I can write this also, the power series. Is called the Taylor series of f around or at around x sub 0. Okay? So for some reason, calculus books insist that if x sub 0 is 0, call it the Maclaurin series. Okay? So if you call all of them Taylor series, nobody bothers. But when you are reading books, sometimes they try to be smart. They say, write the Maclaurin series of this function. Okay, so then it means take x sub 0 equals 0. Okay, so the question is, and okay, so before that, suppose the answer, so we are interested in this thing, okay? So these are definitions, and if the Taylor series of f at x sub 0 converges to f on some interval x minus x sub 0 less than r, then we say f is analytic at x sub 0. Actually, you need to do a few work to show that if we have this thing x sub 0 plus r, x sub 0 minus r. Okay, so inside here, So if the Taylor series converges to the function on this interval, okay, so then if you write the Taylor series of the function here centered at a different point, it will again converge to the function in this interval, in a symmetric interval, okay? But that requires an extra work, and since it is so natural to accept, we accept it without any further remark, okay? So the function f is analytic in this in this region. Okay, so we have C infinity functions, which means that all derivatives exist. And we have analytic functions, all derivatives exist, plus one more condition. The Taylor series we write converges to the function on some open interval. The emphasis here is on open interval. Okay, so R is positive. So there is some non-trivial interval here where the function converges. If the Taylor series is such that this thing converges only at one point, or if this converges everywhere, but it is equal to the function only at one point, we don't like those functions. We don't call them analytic. Okay, so analytic means that you have this freedom of calculation. Okay, so let me see what else I want to tell about this before we start calculating. Okay, so we have to, now we are trying to answer the second question, so we'll look at the remainder. Okay, so suppose the function is analytic. Then this polynomial approximates the function better and better if you increase its degree. Okay, so if the degree becomes infinite, you get precisely the function. But if you stop at some point, you expect that you have a reasonable approximation. Okay? In particular, what happens is that the function approximates, for example, if you take the first term, you get a constant function here, and it approximates the function only at here. Okay? If you take the second one, you get the tangent line approximation. Okay? So it approximates the function in some open neighborhood. If you move away from x sub 0, you get larger and larger errors. Okay, so this phenomena repeats itself. If you take more and more terms, the approximation becomes nicer in larger and larger intervals. Of course, when you take the degree of the polynomial infinite, in other words, if you take the Taylor series, the function is precisely equal to the Taylor series on this whole interval. Okay, so that's our observation. So we say, what is the remainder? Okay, you just subtract t from f, you get a remainder. Okay, so let Rn x be defined as f of x minus Tn x. So we call this the nth remainder. Obviously, most ingenious calculations start with an obvious observation that nobody dared to write down. And f is analytic if and only if limit n goes to infinity r and x is equal to 0. Okay, an obvious observation. This obvious observation would not be any use if we didn't have an expression for Rn. Okay, so that's the big theorem. So big theorem of this thing is the following. So this is called Taylor's theorem. Okay, so this tells us that Rn x is equal to the m plus first term, m plus first derivative, evaluated at some mysterious point, divided by m plus 1 factorial times x minus x sub 0 m plus 1. Okay, so you are calculating the remainder at this particular point x. If you take only the first n terms of the Taylor series, the error you are making will be precisely this number. Okay, x is fixed, you know where x is, so this part is a number, n plus 1 factorial is a number. The only thing is, what is this c? For some c between your x and x sub 0. Okay, so suppose this is x sub 0, this is x sub 0 minus r, this is x sub 0 plus r, and you want to calculate the remainder here, so c is somewhere here. This reminds you the mean value theorem. So in fact, one way of proving Taylor's theorem is iterated use of mean value theorem. So you eventually come to the point that the first n terms is like mean value, is the right-hand side of mean value theorem. Okay, so this will be useful if we have an understanding of the n plus first derivative of a function. Okay, but for some of the very popular functions, this is understandable. When f is sine or cosine, the n plus 1 first derivative is plus or minus sine or cosine. So it's absolute. Well, wherever you evaluate it, it will not be larger than 1. Okay, so this part is less than some upper bound. Then you have a number raised to the power n plus 1 divided by n plus 1 factorial. So this is one of the sequences that looked awkward, but we did it anyway. So we found that this always goes to 0 as n goes to infinite. Okay, so the remainder goes to 0 if the nth derivative is bounded for every n. Okay. One immediate. Okay, so let me write this and then we take a break. One immediate consequence of this, if fnx is bounded by m on some interval, okay, so instead let me write this one, on x minus x sub 0 less than r, then f is analytic there. Okay, why? Because we calculate the absolute value of this for an arbitrary x. Okay, so this is precisely equal to this thing, n plus 1 evaluated at some c, n plus 1 factorial times x minus x sub 0 n plus 1. Okay, but this one, no matter which derivative I take and no matter where I evaluate it, it is strictly less than 1. So this is less than m times I have x minus x sub 0, actually absolute value m plus 1 over m plus 1 factorial. Okay, so we know that this goes to 0 as n goes to infinite. Okay, so limit as n goes to infinite. Okay, so I'm taking n goes to infinite from here of r and x is equal to 0, and by definition f is analytic there. Okay, so next R will exploit this fact. Okay, any questions so far?